Well, my watch says it's 5 o'clock, so let's get started. Good evening, everybody. My name is Charles James. I'm a member of the board of the Friends of the UW Libraries, and in that capacity, I want to welcome you to tonight's event. Before I introduce tonight's speakers, I need to put in a word from our sponsors. For over 75 years, the Friends organization has been championing our excellent library system here at UW-Madison. We are an all-volunteer organization that strives to bring visibility to campus libraries and the world-class collections that they hold. Our activities are made possible by donations, both in the form of monetary contributions and in the form of donations of used books. Twice a year, the libraries hold a book sale. The most recent one was, I think, while I was in Italy. It was a week or two ago. The most recent one, I say, was recent. If you have books that you no longer need, consider donating them to the UW Libraries. You might not want to contribute tonight's book to the book sale just yet, but if you have others, please consider giving them to us. Your contributions support grants to scholars from around the world who use our collections in their research. They also support evenings like this one. But enough of the commercial pitch, let's get to tonight's book, Chasing the Stars: How the Astronomers of Observatory Hill Transformed Our Understanding of the Universe, and I see they've extended it a bit to science and culture. It is my pleasure to introduce you to two authors who have put UW-Madison on the map in a unique way. Anybody who has visited Madison may have noticed that dome structure at the end of State Street. No, I'm not talking about the Capitol. I mean the Washburn Observatory on Bascom Hill, just up the hill on Observatory Drive. Our authors, James Lattis and Kelly Tyrrell, have done extensive research not only on the observatory itself, but on the many men, and especially the women, who have contributed to the development of astronomy as an academic field here in Madison and around the world. You will find lots of technical terminology in the book, yes, but more than that, we learn the stories of the individuals who made it all possible. Our authors are eminently qualified to write such a book. Jim Lattis is a member of the Department of Astronomy, but is also the director of Space Place on the South Park here in Madison. Those of you who've gone along the bike trail will probably also see his contributions, because all the little vignettes about the planets you will see, starting with the sun at Monona Terrace and ending with Pluto out in Mount Horeb. His colleague, Kelly Tyrrell, is Assistant Vice Chancellor for Content Strategy in the Office of Strategic Communication. I'm tempted to read their biographies from the back of the book, but I'll let them tell you more about themselves. I do want to say at this point, however, the book is excellent. It is written with the expert in mind, yes, but it is perfectly accessible to the layperson. I encourage you all to purchase a book and read it from cover to cover. In the meantime, it is my pleasure to turn the podium over to Jim and Kelly. Jim and Kelly?
Thank you, Charles. And thank you for everybody here tonight. Whether or not you have read the book yet, it hasn't been out that long. Hopefully there is something new you learned tonight, and maybe it inspires you to pick up the book or share with somebody else something that you've heard. A little bit about us, maybe to start. Jim and I have been working together for many years now. I think we've lost track. A little bit of an unconventional pairing. I have a background as a scientist, cell and molecular biology. So if you read the back of the book cover, I say I started my career looking the other way, down the microscope. But transitioned into a career in science writing, had the privilege of going to South Africa, visiting the Southern African Large Telescope, getting an incredible view of very dark Southern Hemisphere skies for a large reporting project for the university called Origins. Jim and I had already been partnering for, I think, a couple of years at that point. Anytime there's an astronomical phenomenon in the world that somebody has a question about, Jim's just an incredible resource. How many television interviews have you done at this point, Jim?
Lots. I have no idea.
And so, if there was a meteor shower or a new comet, Jim would often offer to write a blog post for the university, for our office. And I would work to edit the blog post and turn it into something that, maybe a historian is interested in, but somebody who's not a historian might also be interested in too. And that's really sort of the genesis of this book. Jim did a lot of the original research and sifting through the archives, and so questions related to that are going to be best suited for him at the end of the talk, but we worked together to really help turn a lot of the essays and the historical and archival material into good stories for the book. So with that, let's get started with a little bit of history about Washburn Observatory, which, believe it or not, shock, has its origins in the early notions of the Wisconsin idea. So in the mid to late 19th century, having an observatory was kind of like universities today having computer science centers. It was really a way for universities of the era to establish themselves as research universities. In fact, this period, 1840 to 1890, has actually been defined by historians as the American Observatory Movement. So it was John Bascom, who here has heard of John Bascom? Shocker. Shortly after he arrived as the 6th president of the University of Wisconsin, he really sought to make UW a research institution. He promoted the public service role of the university and really admired the research institution model at places like Harvard and Michigan and Cornell. He believed that building an observatory was, quote unquote, the perfect project. And it turns out former Governor Cadwallader Washburn agreed with him, and he was willing to help him build it. So Washburn had become a very rich man. He had a lucrative career in banking and as a land agent. He helped found the Wisconsin Historical Society, thank you, Governor Washburn, and his milling business would go on to become a company we're all probably familiar with today, General Mills. Washburn was also a regent of the university, and he provided the funds to build and equip Washburn, the observatory, not himself. Just a quick show of hands. Who has been to Washburn Observatory? Excellent. We're going to cover this later, but the observatory has a very long history of being open to the public, and Jim is really responsible for sort of the modern era of public observing nights, and we'll talk more about that in just a bit. So in 1876, though, Governor Washburn and Bascom were able to convince the state legislature to provide funding to the amount of $3,000 annually to support and maintain the observatory. But of course, as we all know, there were conditions. The observatory had to be donated at no cost to the state. So the state would help fund it, but only if they got it for free. I like to point out that it is the first public-private building on the University of Wisconsin campus, all the way back to 1880s. So by 1881, what we had was a really well-equipped observatory run by a stable institution with a dependable, though not overly generous, budget. But it was guaranteed by state statute. Bascom himself, though, could not have known what the observatory's earliest science would ultimately lead to.
Thanks, Kelly. So not surprisingly, the goals of an astronomer in the 1880s are pretty different from the way the science of astronomy looks today. And the early astronomers there were pursuing research that is sometimes today thought of as the old astronomy, although it really lays the foundations for what we think of today as astrophysics. But the observatory was very well equipped for this quote-unquote old astronomy, which actually was known by its practitioners more as the astronomy of precision. That's quoting George Comstock, who was the third director of Washburn Observatory. We're not going to go through the sequence of the directors. I think they'll all get mentioned at one point or another, up to a point. So the astronomers in those days were looking at making measurements, position measurements primarily, of the sky. The other thing that astronomers would do is look at planets and look for features of planets, for example. But in those days, in the late 19th century, the nature of stars, for example, was completely unknown in the sense of how they might generate their energy, how physically big they might be, how massive they might be. And looking at the positions of stars, measuring the positions of stars, was important in part for creating things like star catalogs, but in part for finding their motions, various sorts of motions that the stars are exhibiting for a number of reasons that give us insight into some problems, like the motions of binary star systems or the overall motions of stars called proper motions of stars. These are all glacially slow sorts of measurements. And there were special equipment, special telescopes and special instruments at the observatory to measure these very tenuous, these very small quantities to as much precision as they could, hence the astronomy of precision. And usually the precision was achieved by multiple measurements, that is repeated over and over and over again, measuring the same binary star system over and over again for not just years, but decades. So these sorts of things, though, lay the foundations of a number of important problems in astrophysics, in the astronomy that would come along. Astrophysics would use a new set of technologies completely, and Washburn Observatory played a big role in that, in one major aspect of the development of several, but in the technology of astrophysics. But some of this science that was being done in this eyeball at the eyepiece kind of era, when the astronomers these days get to sit in warm control rooms and look at computer screens and even receive their data the next morning in email. Comstock and astronomers of that era sat up all night looking through their telescopes with their eye at the eyepiece. It was the only way to make the observations. They might be accumulating data that would eventually yield, say, the masses of the stars in a binary star system. That's a fundamental piece of information. You're not going to understand how stars work until you have that, among other sorts of things. And the motions, those motions measured decade after decade, would eventually reveal the masses of stars. You also need to know the distances of stars, and there was a special telescope at Washburn Observatory for making measurements of what's called stellar parallax that, again, repeated over and over again for many years, drives the noise down, gets you the precision you need to calculate how far away some stars are, nearby stars. In fact, at one point, when the distances of only about 100 stars out of the hundreds of millions of stars in our galaxy, about 100 star distances were known, and about half of those came from Washburn Observatory, eyeball at the eyepiece astronomy. And another example, the one that's actually illustrated up here, is the overall motions of stars across the sky. The farther ones, the more distant ones, are going to be moving slower for the same reason when you're driving along the highway. The distant objects move slow and the nearby objects move fast. You can very roughly estimate the distance of the stars from their proper motions, their motions across the sky. George Comstock spent many years measuring those proper motions too. And by looking at the populations of stars and how their motions related to their brightnesses, astronomers were trying to figure out the distribution of stars in what we would now call the galaxy, what they tended to call the stellar universe, because galaxies were the word galaxy meant something different in those days. So these were the sorts of measurements. This is the sort of science that was going on. The illustration here just on the right shows a filar micrometer at the end of the Washburn telescope. And that's the sort of instrument that Comstock would have been measuring with all night. So this was a kind of astronomy that was typical of the era. The Washburn Observatory was very well equipped and very productive, and an important part of the science of those days that went up until the early part of the 20th century.
So in the 1870s, this precision science that was happening at Washburn Observatory actually helped support a number of industries that had a need for accurate time signals. That included businesses like banks, courtrooms, not a business, but important, jewelers, railroads. Several observatories across the country could keep accurate time by measuring the meridian transits of stars. Some of these observations that the astronomers were spending all night making, sitting in that eyeball to eyepiece way. And they found these observatories, including Washburn, found they could earn revenue by selling time. So they could keep the time by the stars, and then they could turn around and sell that. The most lucrative customers for observatories in this era were railroads, and they'd pay a few $100s a year for the service. Turns out it's important to keep your trains running on time. Washburn developed a time service under its second director, Edward Holden, who arrived in Madison in 1881, following the sudden death of the observatory's first director, whose name was James Watson. Holden convinced Governor Washburn to purchase for the observatory the clock that you see on the far left here. This is the Howard Mean time clock. Oh, and the guy in the photo, that's Holden himself. This clock was the main clock for the time service. It kept accurate time and relayed signals via telegraph through electrical signals at the top of the clock cabinet. The clock, a little hard to make out, but in this far right, this sort of sepia toned photo here, this is the Hovu clock, and this was actually the one that was being set according to the observatory's measurements. So it was literally keeping time by the stars. In the photo next to that sepia tone is actually astronomer Charles Morse Huffer with a woman who unfortunately we don't have the identity of, but they are actually working at the clock there. So around its peak in 1887, the peak of time service, that is, Washburn was one of 5 observatories that dominated this service in the U.S., and 3 of those 5 were actually based in the Midwest. They included Carleton College, Washington University, and University of Wisconsin. The observatory at Carleton College in Northfield, Minnesota. Who's been there? Anybody been to? Yeah, excellent. And this is actually a photo here I took this summer. I happened to be on the Carleton campus and had to take a picture of the observatory. So Carleton, according to a February 1882 letter in UW archives, had an agreement with Washburn, and I will read that for you here, and that is that Holden agrees with W.W. Payne, director of Goodsell Observatory, Carleton College, that Washburn time will only be sold east of the Mississippi, leaving the west to Carleton. They had a deal.
Non-competition agreement.
I don't know what would have happened if somebody violated it, but I probably don't want to find out. Also from the Lick Observatory archives, we know that Holden offered time services for smaller businesses, also for the state Supreme Court, and even to the offices of the Wisconsin State Journal. Governor Washburn, unfortunately, died in 1882, and he left no provision in his will for the observatory. So again, we have the guaranteed state funding, $3,000 a year, but there was no other money coming into the observatory or into the university for the observatory. So the time service actually became Washburn's observatory's primary source of revenue for many years, and it covered the salaries of its astronomers and also a student assistant who would tend to the clock and telegraph operations. By 1900, though, railroad income had become pretty negligible, and Joel Stebbins became the final student assistant in charge of the time service. Now, Stebbins is important because by 1922, he becomes director of Washburn Observatory. By this time, though, radio signals have begun to replace telegraphic signals, and so the observatory's role in selling time was virtually over.
So Stebbins is a nice connection between these two eras. He obtained his early training at Washburn Observatory. He was a graduate student for 1 year here in the academic year 1900-1901. And after that, Comstock, who was actually the dean of the UW Graduate School, decided that Stebbins was a talented enough student that he needed to go to a major observatory and get a PhD. So he went to the University of California and Lick Observatory and got his PhD there. Stebbins then, right out of graduate school, got a job as a director of the University of Illinois Observatory, where he started collaborating with a physicist there, who was a man named Jakob Kuntz, a physicist, a European physicist, emigre to the U.S., and was up on the latest science of the day, things like the early days of quantum mechanics and general relativity. And one of the things that played a big role in the science of understanding quantum mechanics was something called the photoelectric effect. And Kuntz had developed a new kind of light detector called a photoelectric detector. Used the photoelectric effect, which was studied very much in the laboratories, but used it for this practical purpose of measuring the intensity of light sources quantitatively. And Stebbins saw in that a new kind of astronomical instrument. Now, Stebbins, again, had been trained here at Wisconsin for a little while, where Comstock and his predecessor, James Watson, were both prolific and inventive instrument builders. Some of these instruments were more successful than others, but they were constantly trying new ideas. And Stebbins picked up that ethos, perhaps certainly here at some level, and then probably also at Lick as well, and put it to work at Illinois, where he developed these photoelectric photometers that could detect starlight, very small amounts of light, and detect the variations in, for example, variable stars. Now, astronomers could do this photographically, but the precision was low because they were taking a photograph and then measuring the size of a dot that the starlight makes on a photographic plate and trying to infer the brightness and differences in brightness from the sizes of these chemically produced spots on photographic plates. Stebbins was able to develop instruments first of all at Illinois that could measure much more accurately the light differences of stars. In particular, the first problem that he applied it to was variable stars. So one of the things you see up here, that's Stebbins, by the way. That's Stebbins at Washburn Observatory, where he came in 1921. Well, 1920-21 was a transition year. He was director then of Washburn Observatory, succeeding his teacher Comstock, but he brought this new technology from Illinois. This is a light curve on the lower right showing the light variation of a particular star. And this kind of data is a completely new kind of data because the photographic photometry could not achieve the level of precision that's represented there. Those kind of measurements allowed him to actually infer the physical nature of binary star systems, things that we can't see in the telescope. So there you see a sketch from one of his articles on the left there showing the structure of this star system, a dim one and a small one of which occults or eclipses the other, so they're called eclipsing binary systems. This was a new sort of thing that was derivable from the technology that Stebbins brought to Wisconsin from Illinois, and then improved enormously in terms of its versatility and sensitivity here, again by working with physicists in our physics department. And he found new applications for it, which include, as it says up there, color index measuring of stars, which allowed him to get a quantitative measurement of the color of a star. Some stars are more reddish, some stars are more bluish, but quantitatively, how do you compare those? With his photometers, he could derive this color index and actually plot the rednesses of stars. And that led to the recognition that some stars are redder than they should be, because the spectrum of a star also tells you the color of a star. So if you see a star with a spectrum that tells you that's a blue star, but it looks yellowish through your telescope, then it's redder than it should be. And it's redder because of the medium that it has passed through on its way to us, the interstellar medium, which was generally presumed to be a vacuum in those days. Stebbins was able to show that not only is it present, but it strongly affects the coloring of stars, and it allows you to get then more accurate distances to stars. And this led to some dramatic conclusions. There's a memorable day at the observatory when it's recorded in an oral interview of someone who worked at the observatory that Stebbins came out of the office and announced, "We shrunk the universe." He's using that word in a sense that we don't use it in anymore. In those days, the universe meant the stellar universe, all the stars that we see in the sky. Once again, the existence of galaxies as independent comparable galaxies to our own was still in its infancy at that point. Stebbins had been able to correct for the interstellar extinctions that other astronomers were neglecting completely, and realized that previous ideas about how large the stellar universe is, our galaxy that is to say, were too large by somewhere between a factor of 2 and 3, depending on exactly which numbers you used. So that's still the number, that the galaxy is about 100,000 light years in diameter. If you look up in a modern astronomy text, that's the number you'll find. On top of arriving at the correct size of the galaxy that we live in, Stebbins was also able to show that it is our galaxy is qualitatively different than previous descriptions, which had basically assumed that they were a transparent cloud of stars, but that there's a huge amount of obscuring matter, the dust and gas, in the disk of our galaxy, which Stebbins liked to liken to the ham on a ham sandwich. You can see this ham sandwich effect there, the slabs of bread on above and below, and the ham right through the middle there is the dust and gas disk of our layer in our galaxy, which is not only important for being able to make your measurements accurately, that's where stars come from, and that's the material where stars go back to when they explode and otherwise expire. So Stebbins had discovered the raw material, discovered and mapped the raw material that is an intrinsic part of the activity of galaxies as we understand them today. So these were major insights that were coming out of this new technology up there on the hill at Washburn Observatory.
And they ended up really important to the future of modern astrophysics, if that didn't come through clear, and I'm sure it did, but I think it struck me that I had no idea that humble Washburn Observatory was responsible for making such important scientific advances. So while the astronomers were shrinking the universe at Washburn Observatory, the students were necking on the hill. Cars became popular on campus in the late 1920s, and the road to the observatory soon became a well-known lover's lane. By 1932, a Time magazine article about Joel Stebbins opened with this line: "University of Wisconsin-Jackson Jills like to go up Observatory Hill at night." So in 1934, with composer Harold Spina, and I apologize to any musicians in the room if I butchered that name, lyricist and former UW student Johnny Burke wrote the song you're listening to right now, and he wrote it for the Irving Berlin Publishing Company, bringing nationwide fame to UW's Hill on the Lake.
Or maybe it was infamy.
Maybe it was infamy. Joel Stebbins would agree with that statement. This song was quickly recorded by several singers and orchestras, including none other than Bing Crosby's brother Bob and the Dorsey brothers. This is the song. All of this activity actually came at a detriment, though, to the science, because the scientists depended on dark skies, and it really frustrated Stebbins, who eventually convinced the university to reroute the road and block traffic at night. We're going to get some lyrics here in a moment.
Now it's dark on Observatory Hill. Come on, let's pretend we're Jack and Jill. We'll stroll to the hilltop where college sweethearts go to look at the lights on the campus down below. We'll learn what astronomy is for, and we'll learn what the stars can have in store. I know in advance that the moon may mean romance when it's dark on Observatory Hill. And I'd like to recite you...
So importantly, though the automobile wasn't the only transformative technology of the era, Wisconsin scientists were keeping busy with their now redarkened hill.
Yeah, I just wanted to ask, how many have heard that song or some version of it before? Okay, a few of you. It was recorded a number of times after that original recording, and I've talked to students, I've talked to alums who were here in the 50s who remember hearing versions of that song on campus. So it was a bit of the cultural life here as well. Right, so the technology of these photoelectric photometers that I mentioned, this was really an important key to the new era of astronomy that became possible in the 1950s. The local expertise here, Wisconsin was known as the place that you went to learn how to do that you would go to if you wanted to study astronomical photoelectric photometry. And when it became possible to put payloads of instruments into space, which of course happened in 1957 after the launch of Sputnik, and then the whole social movement, social and really the national movement, I should say, to create a space program and find uses for it other than military uses, it became really important for NASA, the newly formed NASA, to encourage instruments of various sorts to be developed for use in space. And one particular astronomer had in mind, who had been at the University of Wisconsin, that's Arthur Code up there, the guy on the left. Art Code, who had been at Wisconsin as an astronomer before being hired away to Caltech. Code was recruited to come back to Wisconsin as director of the Washburn Observatory in 1958. And he agreed to come back, but what he wanted to do was turn the astronomy department at the University of Wisconsin into a space astronomy department, a place where we would develop instruments that could do observations in space. Now, there was a strong motivation for this because the light from stars that we receive here on the ground is very much limited by our atmosphere. So the atmosphere around us is more or less opaque to the infrared, not to mention, to the ultraviolet. It is opaque largely to the infrared, although there's some that comes through. But at the short, the more energetic end of the optical spectrum in the ultraviolet and beyond in, say, X-rays, we get none of that radiation here on the surface of the Earth. And astronomers wanted to study that in order to understand the physics of stars, for example. So Code had in mind adapting the well-understood Wisconsin technology of photoelectric photometry to orbiting instruments. These are days when astronomers were still very typically trained in photographic techniques, which is something that's pretty incompatible. It was done, but it's pretty incompatible with space uses. How do you get your film back to take it to the drugstore if it's in orbit around the Earth? But the photoelectric photometers will send back their data electronically by radio, and that worked out just fine. So NASA, Wisconsin, was an early receiver of NASA money to develop space instrumentation. And there you see the core team of the early space astronomy lab, Art Code on the left, and then Ted Houck and John McNaughton on the right, Robert Bless. Bless and Code were the two on the astronomy of the astronomy faculty. The other two were in the department. And the space astronomy came about in order to develop instruments for a number of applications that included satellites, but also suborbital rockets, and even NASA's X-15. Some of you will remember the X-15 rocket plane that was used as a scientific test bed for Wisconsin instruments that would later be deployed in orbit. Yeah, let's go on. So just to give you some quick examples here, the first major orbiting instrument that came from Wisconsin was on a satellite called the Orbiting Astronomical Observatory, the OAO-2. We can talk about the OAO-1 later if you want. OAO-2 was launched in 1968, and its two major instrument packages, one of them came from the Smithsonian Astrophysical Observatory, and the other came from the University of Wisconsin over here at that time, the Space Astronomy Lab was on Park Street, a highly successful instrument that, among other things, showed the utility of an observatory in orbit and paved the way both in terms of NASA thinking and planning, but also in terms of scientific possibilities for the development of the Hubble Space Telescope. And one of the major instruments aboard the Hubble Space Telescope, which carries five major science instruments. When it was launched in 1990, one of those five instruments came from up over here on Dayton Street at the Space Science and Engineering Center, where the Space Astronomy Lab built the high-speed photometer, one of the major instruments on the Hubble telescope. About that same time, another major instrument flew on the space shuttle. The instrument that you see down here, the big white thing right there, on its backside, you can't see it very well, but the Wisconsin instrument there, which is the Wisconsin Ultraviolet Photopolarimeter Experiment, flew as part of that package on 2 shuttle missions. So these are the largest sorts of projects that came along during the space age, and it continues. There's certainly still a lot of NASA funding that comes to campus, but it doesn't. You don't see here the suborbital rocketry that was important in research and also development of the technologies along the way. So the tradition of photoelectric photometry that Stebbins brought here in the 1920s eventually ended up, that is, the descendants of these sorts of detectors, ended up in space on board these sorts of spacecraft.
Jim didn't say the acronym for the last instrument he showed you.
For the Wisconsin Ultraviolet Photopolarimeter Experiment? Yes, that's universally known as WHOOPI, although there was some controversy about that, but everybody got used to it.
I've seen a great graphic that somebody designed at the time that would not make it past the brand standards office today. Ask me about that later. So while Wisconsin scientists were innovating technology to send into space, we were also finding people to send into space. So I have to point out, being an astronaut isn't necessarily astronomy, although we do have some astronomers who went on to become astronauts or serve in astronaut roles. But it's a nice thing to mention that there have been several astronauts who've come from Wisconsin, some of them quite well known, including this guy in the center, Jim Lovell. He was born in Ohio, but he grew up in Milwaukee in the 30s and studied engineering here at UW. He is well known for helping safely navigate the Apollo 13 command module back to Earth in 1970, and is most famous for being credited with uttering the phrase, "Houston, we've had a problem here." He actually wasn't the first person to say it, he repeated it. Details. Here on the right is Leroy Chow. He's a living astronaut. He's got a Twitter page and an Instagram page. If you're interested, follow along. But he became an astronaut in 1990. He's from Milwaukee. And he was part of the Expedition 10 mission to the International Space Station. He actually became the first Asian American mission commander on that Expedition 10 mission. And then here on the left is Laurel Clark, who called Racine home. She earned 2 degrees from UW-Madison, including a medical degree, here in the 1980s. On June 16, 2003, she left Earth on Space Shuttle Columbia. She was in space for 16 days, contributed to about 80 research experiments that took place on board. But unfortunately, and quite tragically, when the crew was making its scheduled landing back on Earth, the shuttle disintegrated, and Clark and everyone else on board perished. She did, however, send an email to her family right before her death, and I will read you at least a paraphrase of what she wrote. "I have seen some incredible sights. Lightning spread over the Pacific, the aurora australis lighting up the entire visible horizon with the city glow of Australia below, rivers breaking through tall mountain passes, the scars of humanity, a crescent moon setting over the limb of our blue planet. Whenever I do get to look out, it is glorious. Even the stars have a special brightness."
So observing the stars for inspiration or for scientific purposes both go a long way back at Wisconsin. As Kelly mentioned earlier, there's a long tradition of inviting the public up to the telescope at the Washburn Observatory. That goes back to the second director of Washburn Observatory, Edward Holden, the same guy as the time service. Holden was an interesting guy who was very interested in the popularization of science. And when the observatory was completed, and in April of 1881, he published this notice in the local newspaper announcing the availability of the observatory on a regular basis to the public, with the proviso in there that please don't come knocking on the door on other days, other nights. During the days, it was okay. But at night, on the first and third Wednesday nights of the month, the astronomers would open up the observatory and allow the public to view whatever sights there are in the heavens at the time. And that schedule of first and third Wednesday nights open to the public continues to this day. It's the longest tradition that I know of public nights at any observatory anywhere, with the possible exception of the University of Paris, although they're a little hard to pin down. But that continuous tradition has been a very honored tradition here, and today our graduate students carry it forward, opening the observatory when the weather permits. And when everything is working, sometimes things break and have to be fixed. But generally speaking, we keep to the first and third Wednesday nights. Today, in the modern era, expanded to every Wednesday night in the summer, so June, July, and August. So there is a lot of opportunities to go up and look through our telescope from 1879 that Comstock and Stebbins and all those astronomers used. The telescope is also, of course, used, as it always has been, for classes. And you might imagine there was a big demand to look through the comet back in the days of Halley's Comet. Comstock was so besieged by requests to look through the telescope, he had to establish a ticket system. And there you see that students had a special category of tickets there and were to be admitted to the observatory there if they had managed to snag a ticket. I have no idea how those were distributed or anything. But we still do that as well. We use the observatory, that telescope, for our intro astronomy classes frequently.
And for those who might not be able to read that, it says, admit the bearer to view Halley's Comet between 8 and 10 p.m. on Saturday, May 21st, 1910. And it is signed by George C. Comstock, director. Student ticket. I wonder if they were enforcing, if they had whisk cards in that era to make sure you were actually a student. So yeah, public fascination with the sky goes basically as far back as there have been people here on Earth looking up. The mound builders of the upper Midwest are no exception. According to the oral tradition of the Dakota, the Creator shaped the people from clay at the confluence of the Mississippi and Minnesota rivers after their spirits traveled to Earth along a path of stars in the Milky Way. It turns out that this place where rivers converge and connect land and sky remains a really important place to the Dakota and other indigenous people of the upper Midwest, including the Ho-Chunk. And their ancestors 1,000 years ago built burial mounds upon the bluffs. Dakota scholars have identified correlations between the arrangements of the mounds and celestial constellations. Unfortunately, most of the mounds today have been destroyed, though there are still some remaining. Washburn itself was built atop a mound, and Edward Holden, in the first volume of the Publications of the Washburn Observatory, provides a written record, and this is what you see on the screen here. He published the following. These are striking memorials of a race whose language even is unknown, and they serve to show the kind of antiquities which the young communities of the West afford. They should be sacredly preserved for present and future study. Indigenous scholars have connected Ojibwe cliff paintings in northern Minnesota to constellations with names like the Wintermaker and the Great Panther. And Western scientists have described structures such as Woodhenge near Monk's Mound in Cahokia. Who's been to Cahokia near St. Louis? It's an incredible site. Was at the time North America's largest pre-Columbian city, and it remained that way. But Woodhenge served a solar calendar function, potentially, marking sunrise and sunset at the equinox and solstice. Yet others have argued that the series of circles, Woodhenge is a series of circles built from large wooden posts, hence the name Woodhenge. They have argued that it was built to solidify essentially the city's elite and to solidify their social and cultural power by providing a direct connection to the sun. It's clear that some indigenous cultures, modern and prehistoric, have important connections to the celestial realm. I think it's also important to resist the romance that can lead us to overlook the social and political complexity and richness that are part of the lives of indigenous people. Today, people carry the oral histories and traditional knowledge of their ancestors, despite decades of forced removal from the lands by European American settlers. And so it is that much of what we might know about the Midwestern stargazers is unsettled. But there's no doubt that for as long as humans have been on this planet, we've been chasing the stars.
Well, thank you very much for coming this afternoon. And I think Charles is going to take questions for us.
Yeah, we have time for questions and answers. I'll try to moderate it as much as possible. There are probably microphones that go around. So if you have questions, feel free to raise your hand and we'll get a microphone to you. I did have one question myself that came up early on when you started talking. Are there any other observatories like Washburn in the United States that are very much associated with their universities and their studies? I know there are observatories out there that are doing a lot of research, but are there any campus-like university observatories that you could mention?
Yeah, certainly there are, and each one has their own history, their own particular specialties, connections to the history of astronomy. Some more productive than others. A very important one for us is the University of Michigan, which came the University of Michigan Observatory at Ann Arbor, which came called the Detroit Observatory. Very confusing geographically. But that observatory was very important as an early Western observatory and in the development of Michigan as a research university and as a modern astronomy department. So there are a number in the Midwest, but Washburn and Michigan and a couple of others, Yerkes, which is later than Washburn by 10 or so years, a handful of other ones that are really prominent scientifically. Washburn is right in the top rank of those.
And actually, Jim and I this summer gave a talk for the American Astronomical Society about historic observatories that today have been converted into public spaces and continue to do outreach and help inform the public about astronomy.
Thanks for the presentation, Jim. It was fascinating. I'm curious what you know about how the twin curses of LED lighting and satellite swarms have hindered the ability of Washburn to continue to contribute to scientific progress.
Well, so Washburn was really retired as a research institution well before either of those things. Basically 1958 was the year in which research halted at Washburn Observatory, mostly because the university had built a new observatory well west of town. The city lights certainly degraded the ability of astronomers in Madison to work up there. Even worse was the coal smoke. And so the site had actually begun deteriorating in terms of what the astronomers thought of as ideal by the early 20th century. By around 1910, Comstock is angling to try to have the observatory moved out to a more remote area, a little place on the lake called Eagle Heights, is where he had hoped to. But that plan didn't go through for various reasons. So it was the 1950s. Certainly now the city lights continue to degrade the sky up there, but it isn't a question of a scientific problem. It's more that 1879 telescope is in no way computerized or automated. The operator, the person pointing the telescope, has to be able to see things in the sky, and that gets harder and harder just year by year. So that's a challenge for the use of the telescope, but scientifically it isn't an issue. Those are, of course, big scientific issues for serious research operations, but the satellites imminently but that's another matter.
Where is the documentary record located to write this history of the Washburn Observatory?
So, we probably should have said that towards the beginning. So we drew on a number of primary sources, probably the vast majority of it from UW archives, to some extent from the State Historical Society archives. At UW archives, there's a wonderful collection of the correspondence of the directors of Washburn Observatory. Not so much the first director, James Watson, but from the second, from Holden on. there's an enormous amount of correspondence in there that it takes us right on up into the 1950s. That was a major source. Also, the Lick Observatory archives, because there are a number of connections that we didn't go into. That would be another talk we could give, or connections to other observatories. But there are very important and longstanding connections between Lick Observatory in California and Washburn Observatory. So the Lick Observatory archives were really important as well. And then other sources, well, you saw a newspaper item. There was constant news coverage, especially in the early days when the observatory was a novelty. And those things are all now accessible. Well, not all, but largely accessible online. So that's an important source. But also then publications. The publications of the Washburn Observatory came out sort of irregularly, but in volumes that correspond to the research being done at the observatory up until the early 1930s. And pretty much every one of those volumes opens with kind of a what's been happening at the observatory since the last time. So you can trace equipment changes and facility upgrades and even to some extent personnel and things like that. So those are all really important sources, just leaving aside things like reference works and things like that. Those have been the main sources for the history that we put together. Did I forget something?
No, for the most part, I can speak to a little bit of the chapter on indigenous stargazers. There are no written records, but we benefited immensely from actually a landscape assessment that was done by the city of St. Paul in 2020. Really helped. They spent a lot of time doing a lot of oral interviews and gathering information and evidence, and that really helped provide information for our story. I think this book would have taken many, many years if we'd had to sit down with the right elders and other scholars. And there was also a wonderful PBS documentary in March of 2023 where they spoke with an indigenous scholar from the University of St. Scholastica in Duluth, who was really the one to map the constellations at Hegman Lake. They were actually just these images of a panther, of this figure, a man-like figure that was the winter maker, a couple of others, and people scratched their heads for thousands of years what these paintings that are on the side of this bluff on the lake meant. And it was Carl Gauboy is his name, who says he started thinking like a scientist instead of like an artist, and discovered that these were actually representations of what would have been indigenous constellations at the time. I think one of the things that's remarkable to me about this is there are all kinds of different kinds of archival materials, right? Everything from the sheet music to correspondence in newspapers to sort of the physical archives that exist through paintings or even the mounds themselves.
Right. So it's true. We drew on a few experts in various sorts of areas, and their help was important.
Thank you for a wonderful chat and a great book. Could you reflect on how your relationship as writer and writer-editor combinations has changed through the process of the book?
We've been doing a lot more speaking.
Well, it was... So as Kelly mentioned early on, our first collaborations that led to this were more or less blog posts. And yeah, I think at that point we were much more like a sort of a content provider and editor. But somewhere along the way, it occurred to us that there were a lot more of these stories. I had also been thinking for a long time in terms of a history of Washburn Observatory, but in thinking what would be good blog posts, where do we have a good picture, where do we have a good story, we started coming up with kind of a list that now looks a lot like the table of contents of this book. And so we started talking about what sort of material would fill it out. We had some discussions with the press. We approached the Wisconsin Historical Society press, who was very interested right from the beginning, and they had some ideas about what they wanted to see in the book and how it should be structured. So it was really a collaboration in a lot of different ways. And then we took on our various parts. The pandemic figures in there for a while too, which distracted Kelly completely.
It's true.
and gave me time to write. So I had the better of that of that outcome. It certainly has been a collaboration of various different flavors, but it's been a real good one. Kelly brings to her science writing a feeling for how to convey these things succinctly and clearly, and there a number of my complicated sentences got straightened out along the way.
I think we make a good team.
Yeah, so in the race to build the biggest telescope, where were we in the standings and how long did we hold our position?
Where were we in the what?
In the standings among the biggest
Oh,
telescopes.
in the standings?
In the standings, yeah, and how long were we there?
Well, so if you're talking about the early days, one of the things that Washburn had in mind was to create an observatory that would be a world-class institution, which is perfectly consistent with Bascom's agenda as well. And so he specified that the new telescope at the new observatory should be equal or superior to Harvard's. So that's a statement about pretensions. This is where we aspire to be, because Harvard was already a well-known university, research university indeed, at that time, of course. Well, Harvard at that time had the third largest telescope in the United States, with a diameter of its lens, the big lens at the front of a refracting telescope, 15 inches in diameter, which is one down from the 18.5 inch in Chicago and the 26 inch in Washington at the U.S. Naval Observatory. So with the specification to the telescope makers, Alvin Clark and Sons in Massachusetts, to come up with a telescope that was equal or superior to Harvard's, they presented us with an option for a 15.5 inch telescope. And that's what we got. So Washburn paid for a 15.5 inch telescope. Now, and thus Harvard, which had been the third on the list, was pushed down to fourth, and there we were, where we remained for approximately a year until Princeton acquired a 20 inch telescope that pushed everybody down another notch. So those sorts of telescope races, that was certainly a real thing at a certain level. It was also a matter, certainly, of money, but also of the technology of the time. All the glass for all these lenses came from France. The glass makers who made optical glass in France. It was a big challenge to produce an optically desirable, that is to say, a nearly flawless slab, a disc, that could be shaped into a lens, and you need two of them for each one of these sorts of telescopes. So you might have a 12 inch on the shelf, but at Wisconsin they want something bigger than Harvard's. So you're looking for something that's bigger than 15 inches. And Clark must have had something around. It's not obvious that we could have said, well, let's have one that's a little bit bigger, because that might not have been available. It was a matter of what they could produce in France and satisfy the demand of telescope makers. So the 15.5 is partly about just the availability, I think. I don't really know what Clark had on their shelves in those days, but it wouldn't have been a big backlog of discs of that size. So it was probably just the thing that was available that was bigger than Harvard's.
And now we can say that I mentioned the Southern African Large Telescope earlier. That has a 11-meter mirror. So that is now the largest telescope in the Southern Hemisphere for now.
And she mentioned that because we're major partners.
Yes, we're a major partner in it. So we can now say that we at least have a stake in the largest telescope in the Southern Hemisphere.
Thank you. In one of your earlier slides, there's an old photo of Washburn Observatory with what appears to be another smaller observatory, dome structure next to it. What was housed in there, and was there any significance to astronomy research of that building?
Right. So the book, we go into this, of course. There was actually a bit of an observatory complex up there, more than just what you still see today when you go up. In the main observatory building, there was another major research telescope, which I referred to for measuring stellar parallaxes. There was the student observatory that you saw out there, which was planned and started by James Watson, the first director. Although Watson's premature death kept him from completing that, although Washburn then, at Holden's urging, Washburn then paid for the finishing of that observatory. And then there was another building that you couldn't see, you could barely see a trace of it in that photo, that Watson also started, called the Solar Observatory. So there was quite a complex of buildings up there, especially if you include the observatory residence, which was where the observatory director lived. So that's 4 buildings and 5 research telescopes, or however many it ends up being up there. So it was a much more complex operation than you might think right off. And the student observatory was what you might think, a place for training students. But it also became an important part of the scientific work done at the observatory, because the telescope that was in there, Comstock, used it for a particular research program using one of these rather unusual instruments that he created, and produced important results there on some basic some fundamentals of the astronomy of precision using the small student telescope. So it was an important part for a while. That building was moved off of the campus in 1960. It was given to the local astronomy club, the Madison Astronomical Society, and moved to Fitchburg, where it still sits on a hill. And in recent years has been remodeled now by the CEO of Promega Corporation, and it's now a beautifully operating observatory with very modern instrumentation. So it has its own history and now its own modern activity as well.
First of all, of course, just thank you. Not too important, but I guess something that came to mind is, does the observatory still get $3,000 from the state?
No, I think that legislation was outmoded quite some time ago. I don't know when. I mean, the whole way the university is budgeted now, of course, is vastly different. No, there was the formula in those days was that the university got a fixed percentage of a property tax, a certain mill rate, and so however much money that was, that went to the university, and the $3,000 then had to come out of that. So it was not like the university was getting extra money to have an observatory. It was just included in there that a minimum of that amount of money had to go to the observatory for the salary of a director and for the upkeep of the building.
Great question. Thank you all.
Okay, thank you very much.